Please request record position permission from meeting host. You are the meeting host.
You have my permission. How do I?
Thank you.
Would it be easier to just press record, Roger?
I've clicked on allow record.
Okay. Okay, we're recording.
Right.
And that's interesting. It disappeared. Why did it disappear? Okay. There we are. All right. All right. So these are some remarks on that first lecture. After all that reformulating, we end up with this state sum. The minus sign that controlled the determinant permutation sign is now just sitting as a vertex weight minus in between the incoming lines. We have a variable s, and it goes s forward, 1 over s backward, or 1 over s forward, s backward on positive and negative crossings respectively. And you sum over the states, same states as before, looking at where the state markers meet these bits of algebra, which are the vertex weights. So for example, in the case of a trefoil knot, I put the Alexander's markers because you can just read from Alexander's markers what the weights are, these, by just remembering what happens. So with this state, with a forward and an ingoing, you get, and they're all positive crossings, you get an s from one and a minus 1 over s from the other. In this one, you get an s and you get an s, and in this one, you get a minus 1 over s twice, so you add them up, and that's equal to 1 plus z squared, z being s minus s inverse. So that provides a state summation model for the Alexander-Conway polynomial. And this is on the nose. There's no change up to powers of something. If two knots are equivalent, then they have the same polynomial. On the other hand, it satisfies a Conway identity, and that's not hard to see from the state sum. And so you can calculate it by scanning as well. Good enough. Then there's the question of how do you prove that thing is invariant? And you can do that by looking at the combinatorics as well. So I just give you an example of this, of a oriented Reidemeister 2 move, and leave the rest as a large exercise. Here's a Reidemeister 2 move, and here are all the local states that can happen. And they fall into 3 classes. Ones where these 3 are the markers are far away. Ones where these 3 and the markers are far away. There are 2 of them, and they cancel each other out. There are 2 of these, and they cancel each other out. And you're left with these where the markers, if you split along them, give you a smoothing. And so the the result of pulling it apart, the smoothing, is the states of these 2 markers, states of the diagram where the 2 markers are going up, union the states of the diagram where the 2 markers are going down, and each of them contributes a 1 times whatever else is contributed, and that amounts to the proof that that the state sum for the second Reidemeister move is the same as pulling it apart. Similarly for the first move, and a much more complex exercise for the third move. So that's the way it looks. It's interesting to play with this combinatorics for the invariance. Then there was a comment near the end of the talk about what happens if you let S equal to I. And notice what happens if you let S equal to I in the Conway arrangement. Then you have, I don't bother to write weights of 1. Then you have I and I, forward and back, on the positive crossing, and minus I on the negative crossing. And then you can examine what will happen when you do a clocking move, when you do an exchange move from one state to another. And you find out that every time you do an exchange move, there is some power of I that's multiplying the state, maybe, but it doesn't change. So that means that every state contributes exactly the same thing to the sum. And so in absolute value, you just get the number of states. And the number of states for the evaluation of the Alexander at -1 or the Conway at S equals I. And the number of states is the number of maximal trees in a checkerboard graph for K. So that's what we've shown. For an alternating knot, you have an invariant, a simple invariant of the knot, which is just the number of maximal trees. So for example, if you took a trefoil knot and you looked at the checkerboard graph, it's a triangle graph and there are 3 trees. If you took a figure-8 knot, you have this little graph here with 2 edges between 2 points and otherwise looks like a triangle, and there are 5 trees, and so on. So the absolute value of the Alexander at -1 is called the determinant of the knot. And it turns out that it's the coloring modulus for Fox coloring, which we didn't quite mention, but I'll mention it now for the sake of mentioning it. You color the edges of the diagram with integers or integers mod n for some n, and the sum of the 2 undercrossing edges at a crossing is equal to twice the value at the overcrossing, or A meets B and 2B minus A comes out. So you then can try coloring a knot and you find that some modulus is required. You can also prove that this setup is invariant under Reidemeister moves. So for example, trying to color the figure-8 knot, I have a 0 and a 1 and I get a 2 coming out. 2 times 1 minus 0. 2 times 2 is 4 minus 0 is 4. 2 times 4 is 8 minus 2 is 6, and I came round. So 6 needs to be equal to 1 in order for this to work, and it does work at that point, and that's the 5. It isn't obvious without further thought that that 5 has anything to do with counting trees in the checkerboard graph, but it does, and perhaps we will come back to that later. And I mentioned skein theory. Skein theory is more general than the Conway polynomial. Skein theory says you think of decomposing, oh, I forgot to fix a crossing there. Think of decomposing a knot into switched or smoothed and make a non-associative operation out of that. And then the Conway recursion tells you what to do with the sums and the differences in the abstract part by a simple formula. But then it was discovered after Jones that there are more complex formulas, that is, more complex skein relations like this one, which is the Humphrey polynomial. Here you have 2 variables, alpha and z, and this is invariant under the Reidemeister moves and satisfies the axioms in the box. And I thought I would do a little bit about the skeining for the Humphrey polynomial, and Roger's going to talk about thinking of it in terms of braids. Later, I will talk about it thinking of it in terms of state sums. So we'll be dwelling on the Humphrey polynomial a bit, I'm sure. So the first step is to close that relation on an unknot, and then it's switched unknot and a smoothed unlink. And when you do that, you see you get a 1 and a 1 for the valuations and an unknown on the right-hand side. So you get that P of 2 circles multiplied by Z is alpha minus alpha inverse. So that says that one circle next to anybody, by generalizing the argument, will multiply by delta, alpha minus alpha inverse over Z. Quite different from the Conway situation where the value of the delta is 0, but it includes it. If you take alpha equal to 1, then the delta is 0. And then you can calculate by skeining. And I just did an example here, but there are many examples. You can have fun. You should do this if you haven't done it before. Choose a knot, choose the figure-8 knot and do it, or go do the trefoil without looking. But you see, you switch a crossing and you get an unknot, and you smooth it and you get the links. So the first relation is alpha PT is minus alpha inverse equals Z PL. And then the link alpha PL minus alpha inverse delta Y, because it's got two components and it's unlinked, is equal to ZP of one component, so that's just Z. And then plug in, and maybe I made a mistake and maybe I didn't, but you get a polynomial at the end. And then you notice that this polynomial is heavily in the negative degree direction for the alpha, but it's not hard to see from the axioms that if you switch all the crossings in the knot, you interchange alpha and alpha inverse. You leave Z alone, so that if you have a mirror image knot and you evaluate Hom flipped, then you get the same as evaluating it at alpha inverse. But this is not the case. It's not true that if you evaluate this at alpha inverse, you get the same thing, and therefore PT star is not equal to PT, and so T is not equivalent to T star, trefoil not equivalent to its mirror image by skein calculation. And Hom flip can detect lots of mirror images, but not all, and no one knows how to characterize which knots that are chiral, which knots that are inequivalent to their mirror images are seen by Hom flip. So that's a quick remark about Hom flip. I want to go on now to talk about the bracket polynomial a bit. And this is not how the bracket polynomial got thought up, but I can't resist showing this to you. David Evans showed this to me many years ago, the book by Romilly Allen on Celtic knot tying and Celtic knot design. And on page 259, he remarks how to design Celtic knots. And his remark is summarized in this little diagram here. He says, draw some nice rectangular pattern like this, and then replace the crossings either with smoothings in one direction or smoothings in the other direction for some of the crossings, and you will arrive at some of at Celtic knot designs. And so that's a method of thinking about how they come about. And you see that here, like this one is certainly obtained from a rectangular lattice diagram by making some smoothings. Well, but that idea didn't come into knot theory until somewhat later and becomes this expansion. So this is a skein type expansion, but simpler than the Humfley. We're going to take unoriented diagrams to begin with. We take a crossing and we smooth it one way and we smooth it the other way and add up. And multiply one of them by A and the other one by B and try to understand when this might be invariant for what choices of A and B it might be invariant. So of course this means you have a larger diagram and you only changed it in these two places. And the rule for choosing A rather than B can be expressed to your taste, but you could say that I'm walking along the undercrossing line and I will see an A on my left and a B on my right. And then when I smooth it, I will take the one where the end, similarly on the other side, you'll see an A on your left and a B on your right. And if you smooth it in such a way that the A's that label these two regions see each other, then you take A. Or you can say, I will rotate the crossing line counterclockwise, the overcrossing line, and that sweeps out two regions, and those are the A regions. Or you can make up your own reason why you choose A and B. So here I've illustrated it. I've labeled the A regions as horizontal, but they are the ones that are swept out by the overcrossing line turning counterclockwise, and the B regions. And then when smooth, the A regions see each other, that's the one that gets the A, otherwise the B. And we're going to define a state sum considerably simpler than the Alexander-Conway state sum. in this case, I take and smooth every crossing in the diagram one way or another, in this case 3 A's. And then I take the product of the A's, the product of the smoothing labels, and I take D to the number of loops in the diagram for a raw state sum. So I count loops and I count the vertex weights, the A's. So in the case of this state, the count is 2 and the KS, the product of vertex weights, is A cubed. And then I take the sum over all of these products. And then you see that it is indeed the case that the formula that you have here is true, because when you expand on a crossing, the state sum, there will be the states that have an A smoothing, and there will be the states that have a B smoothing. The ones that have an A smoothing will all get multiplied by A, and you're left with the states of the smooth diagram. And the other ones get multiplied by B, and you're left with the states of the other smooth diagram. So this state sum satisfies the expansion's gain relation. So you have a well-defined 3-variable diagrammatic polynomial, which has its uses, but our question is, what will happen under Reidemeister moves? So then you can do a small exercise to find out what happens under Reidemeister moves, and that's indicated here below. I have a second Reidemeister move, and I have all the different local smoothings of it. So the state sum is going to be equal to those smoothings that are both horizontal, and that means that the upper one is an A, but the lower one is a B. So it's multiplied by AB, and then the other variations of smoothing become A squared, B squared, and AB. One of them has a loop in it, and that loop will come out and multiply to become the extra loop, and I can collect terms. So I have AB delta plus A squared plus B squared times 2 horizontal lines, and AB times 2 vertical lines. So that's the fact of the matter about this, the diagrammatic polynomial. And if we want it to be invariant under the second Reidemeister move, then we're going to take this part equal to 0 and this part equal to 1. So that's certainly one way to do it. There are some variations on this, which are more or less all equivalent to one another. If you took AB equal to 1, that means that B will be equal to A inverse. And then AB multiplies D to be a coefficient of 1, and the D will be the negative A squared negative B squared, and that makes D equal to negative A squared negative A to the minus 2. So we can choose it that way, and then it will be invariant under the second Reidemeister move. And now a nice miracle occurs, because it is now automatically invariant under the third Reidemeister move, as seen by the next little derivation on this slide. Expand the third Reidemeister move picture by the crossing at the bottom, and it smooths horizontally and vertically into an A and an A inverse. The vertical smoothing doesn't change the diagram. Nothing changes if I take this arc and push it down a little bit. But here, I have the permission to push this arc down because it's invariant under the 2 move. And so I can push it down into the middle and then push it a little further, and it ends up below. And now you see there is this site and this site, and you can put it back together, and it becomes equal to the evaluation of the knot after the third Reidemeister move has been applied. So that means that this is invariant under second and third Reidemeister moves. It's not invariant under the first Reidemeister move. The general picture of what happens under the first Reidemeister move is here at the bottom of the slide. I'm assuming you can see the arrow I'm moving. If we expanded this by A and then by B, you get a loop. So you get AD plus B multiplying no curl at all. And AD plus B in this case will turn out to be minus A cubed if you use the specialization that I chose. So it multiplies by minus a cubed in one direction and by minus a to the minus 3 in the other direction. And you can then normalize it by multiplying by a power of that to get something that's invariant under all three Reidemeister moves. Or you can say to yourself, I have a polynomial here invariant under R2 and R3 and work with it in that category of moves, which we usually call regular isotopy. So that's a capsule picture of the bracket polynomial. And here's a picture of lots of states in the case of the trefoil knot. In general, there are going to be 2 to the n states where, when the knot has n crossings, of course, and they're all laid out there at the bottom of the slide. And each one is contributing what it contributes. So for example, this one contributes a squared b. And I'm going to normalize it so that a single loop is just 1, but 2 loops will give me the delta. At least I usually normalize that way. So the unknot has 1 for its value. And so each of these contributes and you can add up and get the polynomial. It's worth mentioning that a little reorganization of these states is very important, and we'll come back to it. The reorganization is sometimes called the Krovanov complex or the Krovanov category. Better said category here because it's just arrows and objects and nothing else. I've written the states again, and I have an arrow between one state and another if an A smoothing turned into a B smoothing as I walked along the arrow. So I started on the left with all A's and I ended up on the right with all B's, and I have 2 columns in the middle. In the first column, there's 1 B only. In the second column, 2, and in the last column, 3. And this is a category, and it would be a category, rather, if you added an identity arrow to each object, the states being the objects, and took all the compositions of arrows to be generating the morphisms in the category there. And you could ask, as Krovanov did back around 1998 or 99, could you measure the category and get a finer invariant than the bracket or the Jones polynomial? And the answer is yes, and that's a long story, which we won't do today. But it's worth going into, and we will talk about it. Let's look a little bit at some of the calculating for the bracket. The normalization that I mentioned a few minutes ago is as follows. F sub k of a is minus a cubed, that's the value of a positive loop, raised to the negative writhe of k and multiplied by the evaluation of the bracket, where the writhe of k, W of k, is the sum of the crossing signs of the knot. So here's a trefoil knot, all plus signs, and the writhe is 3. And then you will have no trouble checking that Fk of A is invariant under all 3 Reidemeister moves. And by the time we get to Fk, we have the Jones polynomial with a different variable. And I'll tell some stories about Jones polynomial eventually. We'll stay here with bracket and its normalization. So the calculation, the Blackboard calculations will look like this, right? We have the knot, we have its mirror image. The mirror image evaluated today is going to be the evaluation of the bracket at A inverse, and similarly for the F. So that's just like what happened with Humphrey. You switch to A inverse and you get the evaluation for the mirror image, and we could prove that the trefoil and its mirror image are different by a bracket calculation, just as we did with a Humphrey. What difference is there? Well, the difference in terms of what we've proved is there. We've actually proved, remember, right there, that this is an invariant of the knot. So there's quite a bit more work to be done to prove that the Humphrey polynomial is an invariant. And that's interesting work. The remarkable thing about the bracket state sum is that you can write on a postcard the proof of its invariance. And that it does manage to do things like prove that the trefoil knot and its mirror image are different. So this would look like this if you were working it out. You would start with the knot and you skein it into the two smoothings, and then actually you have a hop-link over here and you skein that into two smoothings, and you have three things rather than 8 things here, because each of these has a little curl left in it, and we know how to evaluate a curl. So I can say immediately, just getting down to these 3 guys, that the bracket of the trefoil knot is going to be a curl evaluation times a squared plus another curl evaluation times 1, a inverse and a, plus another curl evaluation times a inverse. So that looks like this: a squared, curl evaluation 1, curl evaluation a inverse, curl evaluation, and adds up to minus a to the 5th minus a minus 3 plus a to the minus 7. And then normalizing it by using the rive, it ends up at a to the minus 4, a to the minus 12, a to the minus 16. Very prejudiced in the negative degree direction, and so fk star is very prejudiced in the positive degree direction, and we conclude that the trefoil and its mirror image are not the same. At this point, you might wonder, well, how do we otherwise prove that knots are equivalent to their mirror images? And if you're interested in history of this, you can find out that Max Dane around 1905 is perhaps the first person to prove that some knots are inequivalent to their mirror images, and that he proved the trefoil, among other things. And he did it by using the fundamental group of the complement of the knot plus an element of the fundamental group that runs along the knot, a longitudinal element, and watches the behavior of that and makes a proof. It's a very nice combinatorial group theory, and you can find an account of it in Stilwell's book, Topology and Combinatorial Group Theory. It's very interesting to compare these two approaches because they're so different. And in fact, it's very interesting but frustrating to ask the question, what is the relationship between this diagrammatic combinatorial approach to a knot invariant and getting to knot invariance in relation to the fundamental group? We talked about the Alexander polynomial and showed how you could get to it in a combinatorial way, and that indeed it was a state sum, but that Alexander polynomial is closely related to the fundamental group of the knot complement, and I'm sure we'll talk about that more. One doesn't know how the bracket polynomial or the Jones polynomial is related to the fundamental group of the knot complement. And somehow in principle, it should be related to it. It should be derivable from it if you added the longitudinal information, but we don't know anything about that yet. Here's the same calculation that happened on the blackboard as it looks if you typed it out. And then I want to talk about the Temperley-Lieb algebra for a few minutes, and then I'll stop. We got started a little late, but I think it's probably a good idea to stop anyway. Temperley-Lieb algebra it looks like this. And why am I talking about it? Well, I think I didn't include a slide that would explain this so well. So let me use an earlier slide that will show you what I mean. But first, look at this. It's like braids in that you start with some points at the top and you go to points at the bottom. And it's well motivated on its own grounds. What I'm considering are all ways of connecting points to points, either top to bottom or top to top, in such a way that they don't cross one another, so that it's a purely planar algebra. That's what you're looking at here, all the different ways to connect the points that don't cross over one another. And we multiply by sticking boxes on top of one another. So if you were to imagine sticking the U1 box on top of the U2 box and connecting the points in the middle, I'm not going to make the drawing. You would get U1, U2, and you would get U2, U1 if you plug them in the other way. Here I've actually drawn it, so it's worth looking at. If we take U1 and we square it, then here's U1, and then here's U1 again. And you see you get a loop in the middle coming out, and you just get U1 squared is DU1, where D is the value of the loop. If you take U1, U2, U1, then you get U1 back. And they commute if they're far apart. Reminds you of braiding. And in fact, this is part of the story of how von Jones found the Jones polynomial. He was using an algebraic version of the Temperley-Lieb algebra, not this diagrammatic one, but he notices that this is reminiscent of braiding. Now, what does this have to do with what we've been talking about? Well, you see horizontal smoothings in here and you see vertical smoothings in here, but I could have drawn a better picture, but I will go back to this diagram and ask you to imagine that this is a braid. It is a braid. It's a two-strand braid, right? And when you expanded it into the bracket, you got a Temperley-Lieb connection and an identity connection. So if you imagined a more complex braiding where maybe you had a little strand next to it on either side, then you see you would find yourself getting things like this. Suppose that you had a crossing here. Then that crossing could be resolved smooth vertically and you would get an identity element in Temperley-Lieb, or it could be resolved horizontally and you would get this smoothed element in Temperley-Lieb. So you can think of the bracket expansion as a mapping on braids from braids to Temperley-Lieb algebra, where you're allowed to add elements in the Temperley-Lieb algebra. And then you get the following kind of picture. You get a representation of the braid group into the Temperley-Lieb algebra, and then you can go from the Temperley-Lieb algebra to algebra by counting the number of loops you get when you close the top of the Temperley-Lieb element back to its bottom. And that, by that I mean, imagine that you close this top to bottom, and top to bottom. You can see that you would get one loop in that case. But in this case, you get 3 loops. So you can count the number of loops and you can take delta to the number of loops. And so you factor the state expansion and the delta count in this way, from braids to Temperley-Lieb algebra, from Temperley-Lieb algebra to the evaluation ring, and the bracket is the composition of those two. I'll perhaps talk about that in more detail next time, but that now parallels the form in which Jones originally defined the polynomial. And Temperley-Lieb brackets are reminiscent of Dirac brackets. In Dirac, you have brackets like this, which go horizontally. And when you multiply them, they turn into projectors. In this case, half of a bracket like this, a ket bra, would represent a vector. So I have just represented it in an abstract way, so it looks like Temperley-Lieb. And I have another one over here of a different cut, meaning it's a different vector, a covector and vector. And when you put them together in the other way, forming a bracket, that's a scalar. That's just like our loop. So if I take P times P, I get loop times P, just like we did before. But if I take P, QP, then I get another scalar, a funny scalar, and this scalar, and I get the bracket on the outside. So I get that PQP is a multiple of P, and I'll get that QPQ is a multiple of Q. So that the Temporally-Lieb algebra actually reaches all the way back into the structure of simple projectors on vector spaces, and it has a lot of life of its own in some physics directions, which we may also talk about. That's a good place to stop. So thank you for listening, and I hope that all our technicalities disappear into ease of communication by the next time.
Thank you very much.
Yeah, thank you, Lou. Yeah.
Thank you, Lou.
Thanks, Lou. Great.
Yeah, I personally found that that Dirac stuff is amazing. That there's this sort of connection with physics, you know, which gives us a bit of style, I think.
Yeah, style, puzzlement, and new ideas, right.
Yeah.
So the temporally-Lieb algebra sits inside of the projectors of 2-1 factors. Is that what's occurring?
Well, Vaughan came to temporally-Lieb algebra by constructing an algebra that described how factors sit inside one another.
Right.
He has a factor. A factor is a subalgebra of an algebra that's generated by projections.
Mhm.
Never mind the rest of the technical definition, but you have A sitting inside of B, and there's a projection from B to A.
Mhm.
So you form a new algebra, call it C, which is generated by that projection. And now B sits inside of that algebra. And there's a projection from C to B. Then B sitting inside of C, you get a D, which projects to C. And you get this tower of algebras and projections. And it turns out that the projectors in these new projectors in the tower satisfy the Temperley-Lieb relations. Temperley and Lieb discovered their algebra by studying the structure of statistical mechanics models. Vaughan discovered a new version of Temperley-Lieb algebra coming from his tower of von Neumann factors.
Mhm.
And then finding out more about Temperley-Lieb, he exercised his curiosity and discovered that he could represent the braid group to it, and that there were traces on it, which if he composed with those traces would give non-invariance. So this is an amazing example of persisting in curiosity through to discovering new things.
Can I just mention an interesting historical fact? Well, possibly interesting, is that my uncle was at school with Dirac and also Cary Grant.
Let's say that again.
My uncle Boyd.
Oh, your uncle.
Yeah, he was at school with Dirac and also Cary Grant. Make of that what you will.
What was he studying?
Oh, this is junior school.
Oh.
Was that an associative relation, Roger? Does that mean that Cary Grant was at school with Dirac?
I guess so, yes.
I mean, it was the same school. It wasn't a different.
It was the
time.
same school. I'm not sure about the years, but they were both at the same school.
Because that would be a very interesting relationship. If
So
Cary
let's
Grant
see.
was
That
at school
makes
with
you
Dirac.
2 handshakes away from Cary Grant.
Possibly. Anyway, well, thanks again, Lou. And are we still recording?
I believe we are.
Okay, so maybe I should stop recording now.
All right, and I will stop.
Unless anybody's got any more comments to make. No?
Yeah, I have one.
Oh,
Can you hear me?
yeah, we can hear you.
Yeah. Professor Kauffman, you told us that there is no, I mean, there is no known Jones and bracket polynomials from the fundamental group of the complement. I mean, there is. Do we know at least if there are invariants of the knot group or not?
As we defined the bracket, it didn't have anything to do with the complement ostensibly, did it? It is just defined in terms of the diagrams. On the other hand, the fundamental group is defined in terms of the complement. But we know from Waldhausen, for example, that for prime knots, the fundamental group and its peripheral subgroup classifies the knot. So the knot can be completely understood from the point of view of the complement.
Yeah, but this is my point. I mean,
But
do we know
but that means
there are
that
listed
in some
variants?
you would like to give me I would like you to give me a definition of the bracket polynomial entirely in terms of the knot complement, perhaps, but I don't know how to do that.
No, but at least to know if there is counterexamples.
That's one of the mysteries of knot theory. I mean, is that, I divide the invariance of knot theory into either two-dimensional or three-dimensional. The two-dimensional ones you get from diagrams, and the three-dimensional ones you get from its complement in space. Sometimes there's a switchover. I mean, you can define the fundamental group in terms as a three-dimensional object, a three-dimensional invariant, or as a two-dimensional invariant, because you can define it from the diagram. Now, the Lou's bracket polynomial, you can define from the diagram, which is two-dimensional, but I don't know, do you know how to define it three-dimensionally? Well,
the only way we know how to define it three-dimensionally is to go by way of Witten's integral, which I'll talk about. But
you're going to talk about that?
Yeah, I will. But Witten says you perform a certain kind of integral over gauge fields in three-dimensional space, and the knot is sitting there embedded in space. So the definition doesn't depend on a projection. But unfortunately, the integral is also not supported by any formal systems that mathematicians know. I mean, that's a strange situation, right? I mean, it's not such a complicated idea. You integrate, right? You sum over a lot of things, but no one knows how to define those integrals in a way that is satisfactory yet. And so you have a definition based on a kind of carousel that's hovering in midair logically. A carousel that lots of people ride.
Yeah. I mean, the same thing is true when you talk about, I mean, the quandle is very similar to the fundamental group, and that can be defined both two-dimensionally and three-dimensionally. But the biquandle is only definable two-dimensionally, and what's its relation to three dimensions? I mean, it's another mystery, as far as I know. But I mean, that's future.
And that's the way it's been since the 1980s. We've been looking at non-trivial invariants that come from two dimensions, and we don't know how to do them three-dimensionally. I think before that, everybody felt that the true story always comes from three dimensions, and one wouldn't even look for invariants from two dimensions.
Would it be fair to say that a knot crossing is a figment of the projection?
An artifact of the projection, sure.
Right, I prefer to use the word figment.
Well, but then it comes in parallel to figment of the imagination.
Yes.
But lots of things are artifacts of the projection, yeah. And we go ahead and study them, like alternating knots. The alternation is a figment of the projection, or an artifact of the projection. And some people say, oh, but then why is that of any importance, right? It somehow seems to be to consider things like alternating weaves.
Right.
Are there any more questions, or does anybody want to say anything more? Okay, so I will stop recording and wish you all good night.